Welcome to this part of the course. Today we are going to talk about radio receivers. In particular, we will talk about receiver parameters like sensitivity, selectivity, fidelity, and then we will talk about AM and FM receivers, basically focusing on super heterodyne receiver and double conversion receiver. What is a radio receiver? A receiver has a function of selecting the desired signal from all other unwanted signals, amplifying and demodulating it and displaying it in the desired manner. So, radio receiver functions clearly highlight that the major difference between receivers of various type is likely to be in the way which they demodulate the signal. So, demodulator will depend upon the type of modulation which is being used in the transmitted signal, namely it can be amplitude modulation, frequency modulation, phase modulation, or any other kind of modulation which we have discussed so far in this course. So, coming to the one of the most important parameter of the receiver sensitivity. The sensitivity of a radio receiver is its ability to amplify weak signals. It is often defined in terms of voltage that must be applied to the receiver input terminal to give a standard output power measured at the output of the receiver. For professional receivers, there is a tendency to quote sensitivity in terms of the signal power required to produce a minimum acceptable output signal with a minimum acceptable signal to noise ratio. The best way to improve sensitivity of a receiver is to reduce noise level. So, how can we reduce this noise level? This typically can be done by reducing the temperature or the bandwidth of the receiver or improving noise figure. Here in this particular plot, we see sensitivity plot for a AM receiver. Typically, we know the AM transmission or broadcast range is starting from 500 kilohertz to approximately 1.6 megahertz. So, what we can see here is that the sensitivity is given in terms of the voltage, which is the unit here is microvolt, and the x axis is the frequency of AM broadcast, and we can see clearly what is the sensitivity of a typical AM receiver for the given broadcast range. Now, coming to the receiver selectivity, this is another very important parameter of a receiver, and it actually refers to the ability of receiver to reject unwanted signals from the output of the signal. Now, selectivity mainly determines the adjacent channel rejection of a receiver, and it is expressed as a curve which shows attenuation that receiver offers to the signals at a frequency near to the one which it is tuned to. Now, what we are going to see is that later on in the when we talk about different type of receivers, that the selectivity of a receiver is mainly determined by the response of the IF section of super heterodyne receiver, and also on the mixer and RF amplifier input circuits, which play very significant role in deciding the receiver selectivity. The selectivity varies with receiving frequency for ordinary tuned circuits and becomes somewhat worse when receiver frequency is raised. Typically, when the output frequency is higher, the selectivity of a receiver would be poorer. Now, in this particular graph, we see the receiver selectivity for a typical AM receiver which is tuned to 950 kilohertz. So, the y axis is attenuation in dB and x axis is the generator detuning frequency, which is showing the offset with respect to 950 kilohertz. So, we can see that the center value corresponds to 950 kilohertz, where the attenuation is 0, and as we move away from the 950 kilohertz, the attenuation keeps on increasing, we are providing better and better selectivity for different frequencies. The third important receiver parameter is receiver fidelity. Fidelity is a measure of ability of a radio receiver to reproduce the output of the receiver as an exact replica of the signal which was transmitted from the transmitter. Any frequency phase or amplitude variations that are present in the demodulated waveform that were not in the original signal are considered distortion. So, essentially there can be three type of distortions in the communication signal output. These are amplitude, frequency and phase distortion. Now, after understanding the three important parameters of the receiver, we will start looking at the different circuits which can be used for receiving of communication signals. So, typically we are going to have two kinds of receiver, and these are the two most popular receivers which are currently being used in different applications. So, these receiver types are called tuned radio frequency receiver and super heterodyne receiver. The only super heterodyne receiver is used to a large extent today, but it is convenient to explain the operation of tuned radio frequency receiver first, since it is the simpler of the two, and also the existence and overwhelming popularity of the super heterodyne receiver is justified by highlighting the shortcomings of the tuned radio frequency receiver. So, in this particular slide we see block schematic of a tuned radio frequency receiver. So, a tuned radio frequency receiver will have 2, 3 or more stages of RF circuit, and these all are gang tuned, and then the output of detector is fed to a audio amplifier and then power amplifier, which will generate a signal which of desired power level. So, in the tuned frequency receiver what we have is perhaps 2 or 3 RF amplifiers all tuned together, and they are employed to select and amplify the incoming frequency and simultaneously reject all others. After the signal was amplified to a suitable level, it is demodulated and fed to the loudspeaker after being passed through appropriate audio amplifying stages. TRF receivers were simple to design and align at AM broadcast frequencies, which are very low frequencies starting from 500 kilohertz to 1.7 megahertz, but they present difficulties at higher frequencies which are being used for different communication purposes or FM transmission. And the reason for this difficulty is mainly due to the instability associated with the high gain being achieved at one frequency by a multi-stage amplifier. So, if such an amplifier has gain of 40,000, at all that is needed is 1 by 40,000 of the output of last stage positive feedback to find itself back at the input of the first stage, and the oscillations will occur at the frequency at which polarity of this spurious feedback is positive. Such conditions are almost unavoidable at higher frequencies and is certainly not conducive to good receiver operation. In addition, tuned radio frequency receivers suffer from variation in bandwidth over the tuning range, and also it does not have sufficient selectivity at higher frequencies, partly as a result of enforced use of single tuned circuits. It is not possible to use double tuned RF amplifiers in this receiver, although it was realized that they would naturally yield better selectivity. This was due to the fact that all such amplifiers had to be tunable, and the difficulties of making several double tuned amplifiers tune in unison are too great. So, the problem of instability, insufficient adjacent frequency rejection, which is the insufficient selectivity, and bandwidth variation can all be solved by using a second type of receiver which we call super heterodyne receiver. Here in this slide we can see a block schematic of a super heterodyne receiver. So, signals are received by antenna, and we see there is a RF stage which includes some amplification and filtering, and then this signal at the frequency Fs is fed to a mixer, which is also fed with the local oscillator frequency Fo, and the output of mixer is selected to have only the difference frequency, which is Fs minus Fc, and this frequency we call as intermediate frequency, and the circuit from now on is designed for this fixed IF. So, there is an amplifier circuit, there is a detector, then there are audio and power amplifiers, and then the output. The input RF front end stage is gang tuned. So, in a super heterodyne receiver, incoming signal is mixed with a local oscillator to produce sum and difference frequency component. The lower frequency difference component, called intermediate frequency, is separated from other components by fixed tuned amplifier stages set to the intermediate frequency. The tuning of local oscillator is mechanically ganged to the tuning of signal circuit or radio frequency stages, so that difference intermediate frequency is always generated at the fixed value. Detection takes place at intermediate frequency instead of at radio frequency, as in the case of tuned radio frequency receiver. The advantages of having a fixed low intermediate frequencies are following. For a given Q factor, the tuned circuits, the bandwidth is lower, making it easier to achieve the required selectivity. At lower frequencies, circuit losses are often lower, allowing higher Q factors to be achieved, and hence even greater selectivity and higher gain in the tuned circuits. It is easier to control or shape the bandwidth characteristics at one fixed frequency. Also, filters can be easily designed with the desired band pass characteristics, slope characteristics, and impossible tasks for circuits which tune over a range of frequencies. Now, these are the advantages of having a super heterodyne receiver, but it also comes with certain disadvantages. One of that is called image frequency. So, when we do heterodyning, we get, instead of one frequency, two frequencies which produce that low frequency intermediate intermediate frequency output. So, these two frequencies, which can both lead to the same intermediate frequency, are mirrored about LO, and hence the term image frequency is used. The image frequency produces the same intermediate frequency that the desired input frequency produces, and it cannot be removed by using any kind of tuned RF circuits. So, it has to be removed before mixing operation. The primary purpose of RF filter at the input of the super heterodyne receiver is to reject any signal that might be present on the image frequency. Here in this particular slide, we see one example. Let us say the AM receiver is designed and tuned to receive a frequency which is at 1000 kilohertz, and the local oscillator for this is going to be 1455 kilohertz, producing an IF of 455, which is the kind of worldwide standard for intermediate frequency for an AM receiver. Now, what will happen is that if there is any signal present at 1910 kilohertz, the mixer will produce the same output of 455 kilohertz for this image frequency, and these frequency cannot be separated by any circuit which follows mixer. So, it has to be taken care of before giving the signal to the mixer. So, reception of an image frequency is obviously undesirable, and a function of RF tuned circuits ahead of mixer is to provide sufficient selectivity to reduce the image sensitivity of the receiver to tolerable levels. See, we cannot remove the frequency completely, but we can at least remove this or attenuate this frequency to the desired levels. So, now how do we select intermediate frequency? This choice is a compromise between several pressing needs which have to be all met to a satisfactory level. So, what we are going to discuss here is that what is the criteria which must be followed for selection of intermediate frequency. The lower the IF used, the easier it is to achieve a narrow bandwidth to obtain good selectivity in the receiver, and the greater the IF stage gain. Now, on the other hand, the higher IF, the further removed is the image frequency from the signal, and hence the better image rejection. The choice of his IF is also affected by selectivity of RF and of the receiver. If the receiver has a number of RF stages, it is better able to reject an image signal close to signal frequency, and hence a lower IF can be tolerated. If the IF frequency is very low, then the frequency stability of local oscillator must be made correspondingly higher, because any frequency drift is now a larger portion of low IF than of a high IF. The frequency should be free from radio interference. To meet this criteria, what has been done is that these IF frequencies for AM and FM broadcast have been standardized. So, typically we use 455 kilohertz as the IF frequency for AM broadcast and 10.7 megahertz for FM broadcast. Also, the intermediate frequency must not fall within the tuning range of the receiver, or else the instability will occur and heterodyne whistles will be heard. So, as discussed, for the reasons outlined previously, the intermediate frequency is normally lower than the signal frequency. However, the low frequency band, already the input incoming signal is much lower. So, we can select IF which is slightly higher, and the standard broadcast AM receivers which tune to 540 kilohertz to 1650 kilohertz or 6 to 18 megahertz for communication purposes, or European log wave band which is between 150 kilohertz to 350 kilohertz use an IF which is in the band of 438 kilohertz to 465 kilohertz, whereas the 455 kilohertz is by far the most popular frequency, which is the standard for AM broadcast. FM receivers use the standard 88 to 108 megahertz band, and they have an IF of 10.7 megahertz. Now, to overcome the problems of image rejection and selectivity, instead of using a super heterodyne receiver which we call direct conversion receiver, which directly converts the RF frequency to the intermediate frequency, we can also go for several stages of conversion. Typically, we go for a double conversion receiver which uses two stages of IF conversion. The first stage has a higher intermediate frequency which allows for better image rejection, and the second stage will have a low IF frequency which allows for good selectivity. So, going from direct conversion super heterodyne receiver to double conversion heterodyne receiver has a disadvantage in terms of the more hardware is required, but it has advantage in terms of having a better image rejection as well as better selectivity. So, as discussed, in a double conversion super heterodyne receiver, what we do is that we typically choose a first IF frequency which is higher, because the higher the image frequency intermediate frequency is, the further the image frequency will be from the desired carrier, and it will lead to a better image rejection. And the second intermediate frequency is chosen to be a low value, so it will allow us to have better selectivity of the stage and also higher gain. High frequency transmitters have more than 2 stages for even higher selectivity and image rejection. In the next slide, we see one example of double conversion receiver. This is typically used for FM kind of transmissions. So, we have a signal frequency which is from 144 to 148 megahertz. First IF is at 10.7 megahertz, which is the standard for FM transmissions, and then second stage is 455 megahertz, and this will allow us to have a better image frequency rejection as well as better selectivity. So, today we studied two popular types of radio receivers, namely tuned frequency radio receivers and super heterodyne receivers. Tuned frequency receivers pose problems in terms of having circuits which are to be designed to work at wider frequency range, whereas super heterodyne receiver simplifies the job by having a RF front end which can be tuned to frequencies, and then later on frequency is down converted to intermediate frequency which is fixed, and rest of the circuits can be designed for this fixed IF frequency. We also studied the parameters which are important for a radio receiver like sensitivity, selectivity and fidelity, and we talked about the criteria for selection of intermediate frequency of super heterodyne receivers, which is a compromise between the image rejection and the selectivity. For most of the communication receivers operating with higher signal bandwidth and carrier frequency, double conversion super heterodyne receivers are used in place of single conversion heterodyne receivers. Thank you. Hope you would have enjoyed today's lecture.